Hello students, welcome to the class. So today we'll see the thermodynamic NCERT theory part 5 in which we will cover the section 5.3. So this is the disclaimer. If I talk about today's objective, so we've already covered the delta U measurement with the help of calorimeter. Today we will see the delta H measurement using a different kind of setup, but the principle would be same. Now if I talk about the specific topics about the NCERT that we are going to cover, so it is 5.3 which is enthalpy change measurement. Then in that we'll also do a question which is related to your topics, which is already being covered in the previous sessions of the theory. So that is from exercise question 5.8. So it is basically related to enthalpy and some previous knowledge. So you have to know about both of them. So let's start our discussion. We have already seen it in the delta U measurement that how we have used the knowledge of say liquid to determine its enthalpy, and with the help of that enthalpy change, and with the help of that we have calculated the enthalpy change for the reaction. So in that case, one thing was for sure that we have to keep the volume constant. But in the case of enthalpy, what should be the constant? That your pressure should be constant, right? So this is our constant. Now our purpose for the reaction would be to measure the heat change at constant pressure, and now that pressure is generally kept at atmospheric pressure, which is the normal 1 atm pressure that you observe daily. We can look at the apparatus to see how this apparatus help us to keep the pressure at our atmospheric pressure 1. If you look at the diagram that is being given here, all the things that we saw in the case of calorimeter will be same almost. The only difference is that here we are not keeping the volume constant. So we are keeping a open container. You can see it in the diagram that we have kept a open container. The lead is open. So that is keeping the pressure equals to the atmospheric pressure, right? Now, again, we have a thermometer. What is its use? So its use is to calculate the temperature change. We have talked about this. And we have the reaction mixture inside this calorimeter. So we'll call this apparatus as normal calorimeter. We don't put any prefix before this like your bomb calorimeter in the case of delta U. So you should remember both of these terms, calorimeter and bomb calorimeter. Bomb calorimeter is used for internal energy calculation and calorimeter is used for enthalpy change calculation. Now, what was the relationship to enthalpy for the pressure constant term? It was given as enthalpy change is equals to heat exchange at constant pressure. So we have written P in the subscript to represent the constant pressure. Now moving on further, we can look at the calculations. So if we are able to calculate the heat change during the process, then we can calculate the enthalpy change of the reaction. So this is our basic motive. Now to calculate that, we should know two things. So that is prior for any calorimeter. So you should know the heat capacity of the liquid first of all, and the second thing is that you should know the temperature change that is occurring in the system. So for that we have used the thermometer. So on the basis of that, if you know the observed temperature and the heat capacity of the liquid, then we can write the formula for heat exchange at constant pressure as Qp is equals to C multiplied by delta T. Got it? Now, if you know the Qp, we can calculate the delta H as well. What we will do, we will simply calculate the Q here, Q at constant pressure, and then on the basis of delta H and Qp equivalence, we can say that delta H is equals to minus C into delta T. Now, where is this negative sign coming from? So this was also talked about in the case of bomb calorimeter. Since you got this heat as C into delta T for the surrounding from the surrounding perspective. So this is the heat that is gained by the surrounding. But you have to calculate it with the respect to system. So whatever heat is lost by the system that is gained by the surrounding, so the magnitude will be same, but the sign will be changed, right? So therefore we have put a negative sign here. You can see it very clearly, and you can easily analyze the same. Okay, I hope this point is clear to you. So this is very important to understand. So whatever heat change you calculate with the help of what? With the help of the more heat capacity and the change in temperature, you have to take the negative sign of that. And this is very obvious also because during a combustion process, it is always seen that the reaction is exothermic in nature. Now, talking about this exothermic and endothermic, what we can say for the exothermic reactions, we know that heat is evolved and the system loses heat to the surrounding. So, we are just generalizing these two things. This is important to remember. Now, next, QP will be negative in this case, and delta RH will be also negative. So, this is our calorie meter. Our next part is to do a question on the same. So, that is more important than rather than mugging up the theory. So, let us move on to a question. Here the question is related to the reaction of cyanamide. It is written as NH2CN, which is present in the solid state, and this is reacting with dioxygen. So this is basically a combustion reaction. All of this is carried out in a bomb calorimeter, and the delta U for the reaction is found out to be minus 742.7 kilojoule per mole at 298 Kelvin. Now, using this information, you have to calculate the enthalpy change for the same reaction at 298 Kelvin. You have a reaction for the combustion also. You can see that the cyanamide is reacting, ammonium cyanamide is reacting to give us nitrogen, carbon dioxide, and water. So this is basically combustion of ammonium cyanide. Cyanamide, sorry, not ammonium cyanide, cyanamide. Your time to solve this question starts now. So I am giving you 30 minutes, 30 seconds to solve it. Just try to put the values in the formula first, right? So if you are doing it well, then you can solve it for sure. The only part to be done is the calculational part. Yeah, and I hope you can do that part easily once you put the values in the formula. 15 more seconds. Okay, your time is up. So this is a question from the NCRT exercise, which is question number 5.8. How do we calculate it? Let's see. If you have solved it, well and good, just match your answer. If not, just listen it to very carefully. Okay, so this kind of questions are asked in your exam. What are the information that are given in the question? The first thing is the change in internal energy, which is minus 742.7 kilojoule per mole. The second thing is the temperature. You can see that the reaction is carried out at 298 Kelvin. It is mentioned clearly. The third thing that we know is the universal gas constant. It is 8.314 joule per mole per Kelvin. But we are doing the calculation in terms of kilojoule per mole generally. Therefore, we'll convert it into kilojoule per mole per Kelvin. But how we are converting it? It's very simple. We don't have to do anything with the mole or Kelvin. We just have to convert the joule into kilojoule. Therefore, we'll multiply with the factor of 10 to the power minus 3. So this is our given information. Let us move further. Now, what is the chemical reaction that is given? It is the combustion of the cyanamide with the oxygen to give us nitrogen, carbon dioxide, and water. What we can deduce from here? We can deduce the change in number of moles. And which moles? The gaseous moles. If you have done this question already, you know that why we are calculating the change in number of gaseous moles. And if not, you can take this step as a hint and solve the question further. Right? From this point onwards, if you are getting it, just solve it. How can we calculate it? It's very simple. Just add the number of gaseous products and subtract it from the number of gaseous reactants. Now, on the product side, what we have nitrogen, carbon dioxide, and water. Water is present in the liquid form, so we will not take its contribution. We will take only carbon dioxide and nitrogen. Now, one very important thing, your reaction should be balanced in this case. Then and then only you can further proceed with the calculation of change in number of gaseous moles. So, can we balance it, or is it already balanced? Let's see. So, we have one nitrogen, two nitrogens. Yes, two nitrogens on the left hand side. On the right hand side, we also have a molecule of nitrogen. So, again, two nitrogens on the right hand side. So, nitrogen is balanced. What about hydrogen? So, from the cyanamide, we have two hydrogens. And from the water, we have two hydrogens. So, hydrogen is also balanced. What about carbon? Again, from the cyanamide, we have one carbon. And from the carbon dioxide, we have the carbon on the product side. So carbon is also balanced. Last is the oxygen. So oxygen is 3 by 2 multiplied by 2. So that means 3 moles of oxygen atoms. On the right hand side, we have 2 moles coming from the carbon dioxide and 1 mole coming from the water. Therefore, this equation is completely balanced. Now we can calculate the change in number of gaseous moles. From the balanced chemical equation, we can say that the number of gaseous products are 1 plus 1, that is 2. So 1 from nitrogen molecule and 1 from carbon dioxide molecule. So 2 gaseous species are there with 2 as the stoichiometric, 1 as the stoichiometric coefficient. So total number of gaseous product is 2. What is the number of gaseous reactants? So it will be 1.5. Again, we will not take the cyanamide. So these points are very, very important. You can do mistake in including this in your calculation. So always remember to exclude the solid and liquid from this calculation. Now talking about the oxygen molecule, it has 1.5 mole in the reactant side. You can see it is written as 3 by 2, which can be simplified to 1.5 in the decimal form. Now we can calculate the delta Ng. How do we calculate it? It's very simple. Product minus reactant. If you do it, you will get your answer as, so we have got this for the product, for the reactant. So therefore, the delta Ng can be written as the product minus reactant, which will be equals to 1 plus 1, 2 minus 1.5. So that will be 2 minus 1.5. Finally, your change in number of gaseous moles will be 0.5. I hope this point is clear to you. Till this point, I hope you have solved the question also. If not, let us move further. So there is again a small hint for you. So we are calculating the delta U, right? We know the delta H and we have calculated the delta Ng. Isn't it pointing towards a certain formula? Think about it. Now our next part is the main part, which is the enthalpy change equation. You must have seen this equation. Delta H is equals to delta U plus delta Ng RT, and believe me, this is the most important equation related to enthalpy. How are we deriving it? We have seen this in the theory part. We know the total formula, which is delta H is equals to delta U plus delta PV. Instead of PV, we have simply written as nRT. Now, since PV is equals to nRT is coming from the ideal gas law, so we are considering the gaseous molecules change only and not the solid and liquid part. Now, the delta Ng is calculated as 0.5 mole. So, we can put this value in our equation. So, delta U is how much? It is minus 742.7 kilojoule per mole. Okay, I have said that delta H is given. No, delta U is given, right? Delta H is to be calculated. And obviously, we are doing the reaction in the bomb calorimeter, so the delta U will be given. Now, this is 742.7 kilojoule per mole along with the negative sign plus the delta Ng 0.5 R. We have written it as 8.314 into 10 to the power minus 3. Again, remember, so this is written because in kilojoule, because the delta U is given in kilojoule, and generally we calculate the enthalpy change in terms of kilojoule per mole, right? Then moving on further, the temperature is mentioned at 298 Kelvin. Just put all these values and we can calculate the delta Ng RD term from here. First of all, you will get this as 0.5 into 8.314 into 10 to the power minus 3 into 298 Kelvin, kilojoule per mole, not Kelvin, kilojoule per mole. So this will come out to be 1.238966 kilojoule per mole. So this is the value of your first term, which is delta Ng RT. Now put this back in the equation. If you put this back in the equation, which is value of delta Ng RT, 1.238966 kilojoule per mole, you will get upon rounding this to the first decimal place as 1.2 kilojoule per mole approximately. See, we have got this value in kilojoule per mole. Why? Because we have taken R as kilojoule per mole per Kelvin. Now substituting it back into the delta H equation, what we get? We get it as minus 742.7 kilojoule per mole plus 1.2 kilojoule per mole. Now this will be calculated as minus 741.5 kilojoule per mole. So this is our final answer. So we have seen that how do we calculate the value of delta H from the delta U, right? So we use this simple formula, delta H is equals to delta U plus delta NGRT. First, we have looked onto the equation. We have seen that in the equation, we have two sides, products and reactant, and to calculate the change in gaseous number of moles, we have to exclude the water and cyanamide. So if you include your gaseous molecules of the product side, then they are two, which is coming from nitrogen molecule and carbon dioxide. So one from each. And then on the reactant side, we have 1.5 mole because 3 by 2 can be written as 1.5. From there, we got the value of delta Ng as 1.5. Further, we have calculated the value of delta NGRT, which is our whole term. This comes out to be 1.238966 kilojoule per mole. We just finally round it off to keep it as 1.2. And this is a general, I would say, tip for you. If you are calculating it, then try to round it off as much as you can. Okay, so this is very important. Now, don't do this in the case of ionic equilibrium. This is generally used for the enthalpy case and any other, or I would say, thermodynamics structure of atom, but we don't do it for the ionic equilibrium because in those cases, you will see that the options are varying just by small digits, right? So it will be like 0.3 greater than the first one, the second one, like this. Okay, so you don't do in the case of ionic equilibrium. Now, first we have calculated delta NGRT. We have the value of delta U. We put it back in the equation because delta H is equals to delta U plus delta NGRT, and we got it as minus 741.5 kilojoule per mole. With this, we have completed this part. Now, let me summarize it for you. What we have done throughout this discussion of calorimeter. So we have first started from the principle that whatever heat is being dissipated by the system is being absorbed by the liquid. Now the liquid is kept such that your heat capacity is known for the liquid, and the second thing is that the liquid is not allowing any heat to dissipate through the uh, system to the surrounding. Okay, it is stopping it there. Then next what we do for the bomb calorimeter case, we calculated the Q with the help of the heat capacity and the mass of the substance that we have taken and the temperature change. How we were calculating the temperature change? It was very simple. We're using a thermometer. In that case, we are keeping a lead, or you can say we are keeping a bomb, and that bomb is closed from all sides, so the volume is kept constant. So whatever we got it at constant volume, and therefore we got our internal energy change because heat exchange at constant volume is equals to internal energy change. Next, we moved on to the calorimeter, which is our today's discussion. In that case, we saw that if we are keeping the lid open, in the second case, we are keeping the lid open, then the pressure experienced by the sample or by the whole this calorimeter setup is the atmospheric pressure. Okay, if it is atmospheric pressure, then we can say that the heat exchange in this case is occurring at constant pressure. Similar to the calculation of bomb calorimeter, we have the heat capacity of the liquid again. Then we have the mass of the substance that we are combusting, and the temperature change is calculated through thermometer. Put this back in the equation again, you will get it as C delta T. And in this case, since your heat exchange is occurring at constant pressure, therefore your heat change will be equals to the enthalpy change, and therefore we got our enthalpy change. So this is the basic idea for these two chapters that we have studied right now. Thank you for attending the session. This was all for today's class.